Welcome guys, welcome to today's lecture. Now today we shall discuss about quark model. Now before that you should know why this quark model comes into play. For that I need to show you something. See, this table has been constructed by Masons and Baryons. These are the pions family, counts family, eta Mason family, nucleon and other particles. There is something interesting about this table. See, these masses are quite very similar. These are very similar. Now see the neutron and proton masses, the sigma masses as well as xi particle masses. So they have very similar masses, but their charges differs. Next we have very short-lived particles like 10 to the power minus 21 second or 10 to the power minus 19 seconds, whereas we have very stable particles also like this proton and neutron. Okay, actually this table shows the hadron family with some resonance particles. These resonance particles behave differently at different energies, but basically they are same. To classify them properly, Gell-Mann and Niemann classified a particular system called eightfold system. In this system they have arranged all the particles in a particular manner where they form a multiplet, and from the data of the multiplet family then form a supermultiplet. Now what is a supermultiplet? A supermultiplet is a extension of this eightfold classification, where a particular supermultiplet have spin same, but their charges as well as their strangeness quantum numbers differs. We have actually here 2 or 3 pictures which are very important for you. Let's go to them. This is baryon supermultiplet of spin half baryons, and this one is spin zero Mason's supermultiplet. Actually see, this supermultiplet have 8 particles and this one has 9 particles. This one is called baryon octet and this one is called Mason nonet. There are some more pictures I shall show you, but these two are very much important. Why? Because from these 2 pictures you can have a clear idea about the quantum numbers, different quantum numbers of baryons as well as Masons. Now you don't have to cram everything, the formulas, the quantum numbers, no need to cram anything. Only remember some particular formulas, and from these pictures you are very clear about the I3, S, then Y equal to S plus B. Okay, so different quantum numbers are very easy from these 2 pictures particularly, and these 2 pictures will soon explain your quark model also. Okay, this picture, this baryon octet, is quite interesting because here no antiparticle has been included, whereas in this Mason nonet this K naught bar, this K minus, these are the antiparticles of these 2 particles. Now from this baryon supermultiplet it is very clear that only these hyperons are strange particles. They have strangeness -1, the sigma family and lambda naught, and the Xi family have strangeness quantum number -2. From the x-axis, third component of the isospin can be measured very easily. See, these two particles have -12, these two particles have +12, these two particles have 0, and the rest have -1 and +1. Actually, you can also determine from the multiplicity formula 2i plus 1 equals to multiplicity, then I equals to a particular number, and from that and from the number of particles you can easily determine the I3. But these pictures, from these pictures actually you don't have to remember anything. You just remember these pictures and everything will be clear. They are baryons, so they have B equals to 1, Y is equal to S plus B. So for this one, Y hypercharge equal to S, that is 0, plus B, Y equal to 1. For this also Y equals to 1. And for them, Y equal to what? S minus 1 plus 1 equals to 0. So you don't have to cram anything, na? Okay. And from this second picture, this Mason Nonnet picture, you are also very clear about the quantum numbers from here. Okay. Now in my previous lectures I didn't mention this eta dash. Actually this eta dash is a high energy resonance of this eta meson, so I didn't mention it there. Now let's go to next picture, because that one is very interesting. See, I didn't mention about these delta particles in my previous lectures. Okay, I shall explain now. This is also S versus I3 graph, and from them this is actually the super multiplet of 3/2 spin baryons. Actually it is called baryon decuplet. See, there are 12 number of particles here, and that's why it's called decuplet. So from this also you can have a clear idea about I3, S, and then I, then Y, etc, etc. The charges are already mentioned here. Only this omega minus has the strangeness quantum number -3 in among the all particles. Now let's come to delta particles. Actually in your graduation syllabus you don't need the delta particles in details. Actually the delta particles were discovered in mid 1950 by Chicago cyclotron and Carnegie synchrocyclotron. What they have done, they use accelerated pions, mainly accelerated positive pions, and the target was a hydrogen target. Then from the locus of the particles, some new particles have been emerged. They were actually low energy resonance particles of proton and neutrons. More precisely, they have masses way higher than proton and neutron, but behave like proton and neutron. That's why they are called the quantum excited states of protons and neutrons. And the scientists named them delta particles. See, in this picture there are only 4 delta particles, but don't you think that they have only 4 delta particles? They have many more, but they are high energy resonance particles, so we shall not discuss about them here because we don't need them. From the data, the delta baryons have masses C 12, 1 and 32, whereas remember the first table shows the proton and neutron had nearly 938 or 39 MeV per c square. So they are way higher than them. Now these data particles also have some antiparticle states made of antiquarks, but that doesn't matter. You only have to know their names, their charges, and their some of their quantum numbers. From these three pictures, you can have an overview of the whole elementary particle family for your graduation syllabus. You know all of the formulas, you know all of the quantum numbers, so everything is a concise form, is in concise form for your exam purpose. Only you have to know the formula, see the three pictures, everything is ready. But here is some twist. You cannot explain why these multiplets and super multiplets happen only for certain kind of hadron particles. For scientists for their time, they cannot explain this formation of eightfold way or super multiplet systems with the knowledge that only these particles are the most elementary particles. Next, we have a mind-boggling question there, because experimentally the magnetic moment of neutron was found minus 1.913 mu n. What is mu n? It is actually nuclear magnetron H cross by 2 mp. mp is the mass of proton. But by theory then, what happened? I equal to q by t, charge by time period. Now neutron, as you know, neutron is electrically neutral particle, so q is equal to 0. Again, mu varies I. If q is equal to 0, I becomes 0. Then what happened? This becomes 0, I becomes 0, and mu proportional to I, that becomes also 0. These are the theory predictions. But what happened? Mu n become negative quantity, a finite quantity. So the idea that proton, neutron and other hadrons or baryons or everything else are only the basic building blocks of atom, this is somewhat wrong. There may be something more fundamental than them. That's when this quark theory has been proposed by Gell-Mann and George Zwing. Actually, they have proposed in 1963 and 64 era. They have proposed this theory to overcome this problem. Initially, they have proposed about three basic quarks: U up, D down, and S strange quark. Initially, the idea was that the hadrons are composed of only three quarks, U, D, and S. But later, till 1977, there were some experimental evidences that still there are some more fundamental particles are there. Then till 1977, one by one, charm, B for bottom, and T, top, these three quarks were discovered. So number of quarks actually 6. Their charges are like 2 e by 3 or e by 3. These are the fractional charges. These are interesting. I shall tell you later why they are interesting. Now the problem, I equal to q by t. Let it is constructed by UD, for now UDD, then these three charges, but this T1, T2, T3. Now see, these quarks are different from each other, so their time period of revolution must be unequal to each other. So there is a finite quantity. I is a finite quantity, so is mu. Problem solved. So by this problem was solved. Now for the properties, you have to know that since they are baryons, actually for baryons, 3 quarks made a one particle, one baryon. So B for each quark equal to 1/3. If they are antibaryons, then they are antiquarks. So the baryon number of them, or the antiquarks, minus 1/3. Now we have y equal to s plus b. So other than strange particles, we have y equal to b. Then other than strange particles, we have what is y, that is the number of b. So if b is 1/3, then y is 1/3. If b is minus 1/3, then y is minus 1/3. But for the strange particles, we know their strangeness quantum number, and we can easily calculate y from them. For an example, for the particles, those have s equal to -1, we have y equal to -1 plus 1/3. For a baryon, minus 2/3. So now we have this picture. Now this picture and this picture is very important. Actually, what I have shown you before was the incomplete picture for according to me, because these two pictures are very much important for your exam purpose. Why? Because in this picture there are there are quark contents also. This is the baryon octet. This is not actually a meson on it. This is a reduced form of meson on it actually. I shall explain later why it is like that. So you have to know only the quark content of one particle, and by this scheme you can easily determine what the quark contents of other particles are. Now see, from horizontally, if you go from right to left, u changes to d, or left to right, d changes to u. And similarly, if you go from this to this type, u changes from s, or this to this, s changes from to u. Now according to this scheme, you have to cram the quark content of p only, u, d. Now you are going right to left, so 1 u will be changed to d, so u, d, d. Okay. Now see carefully, we are taking this path, so we are taking this path, so d will be converted to s, so this is u, s. Now from this one, we are going from right to left, so 1 u will be converted into d. See, this is uds, this is also uds. Then again we are going from right to left, then again a u will be converted to d, ds. Now from there we are taking this path, that is this path where u become s, so u become s, it become uss. Now we are going from right to left, so u become d, that is dss. Clear? I know initially it become quite a bit tough, but after seeing 2 or 3 times you can easily know that. And using the same scheme, we can evaluate the quark contents of meson. But for meson, quark contents are only 2, one quark, one anti-quark. Here also you have to cram only one quark content, US bar, suppose. Then from this to this become DS bar. From this to this scheme, this become UD bar. Similarly, this become DU bar. Using this scheme, U to S, this become SD bar, and using this scheme, that is UD, that D become U, so it is SU bar. So from these two pictures you can easily know the quark contents as well as the different quantum numbers of these elementary particles. But see, there is two particles missing. One is pi naught and two is eta naught. I am not talking about eta dash. So pi naught is actually, you have to cram these two actually here, because I cannot show you the details mathematics why they are like that, why they are not like any other type of combination of U and D. I cannot show you here because it's way complex for your syllabus. So pi naught equal to UU bar minus DD bar by root 2, and eta naught equal to UU bar plus DD bar minus 2 SS bar by root 6. So you have to cram only 4 quark contents: the proton, UUD, the K plus US bar, the eta naught and pi naught. And from this data you can derive all the quark contents of all the particles. Isn't it interesting? Now let's see this picture. I know you can derive all the quark contents like I have told you before using this UDS scheme. Try to assimilate this at your home. If you find any problem, then let me know in the comment section. Now, what about this quark content? See, delta plus have 3U, delta plus have 2U, like the sigma particles have DD or UU. So what are the quantum numbers of them? Naturally, quantum numbers of U are same. So for them, don't you think that this and this have same quantum number? But Pauli's exclusion principle tells you that no particle can exist with 4 same quantum numbers. But see, same quantum number, all 3 particles, UUU, UUS, 2U, same U. So this is a violation of, this is a violation of Pauli's exclusion principle. Now quark model is experimentally verified, but theoretically it is now violating the exclusion principle. What next? Now to solve this problem, we have a new theory, color hypothesis. Now to overcome this problem, scientists have assigned the quarks different colors. Greenberg introduced first this color hypothesis. He suggested that each quark flavor has a particular color, a particular degrees of freedom. This is an inherent property, hidden degrees of freedom. This degree of freedom is called color. What color? For quarks, there are 3 quarks. So he assigned red, green and blue, RGB. And for anti-quarks, he assigned anti-red, anti-green, anti-blue. If you follow the color wheel, anti-red is opposite to red, that is cyan color, anti-green is magenta color, anti-blue is yellow color. In some of your textbooks, you can have cyan instead of anti-red. But generally, we use RGB for quarks and R bar, G bar, B bar for antiquarks. Now there is one more quantum property, the inherent quantum property, that is different from each other. 2U cannot be same, 2D cannot be same, because they are assigned different colors. But like photography in optics, this RGB, what this R plus G plus B means, a white color. That's why according to color hypothesis, an atom is colorless, or the elementary particle is colorless. But don't you think that quarks are like this? This is R, this is G, and this is blue. This is blue colored quark, this is red colored quark. No. If you are thinking like that, then you are completely wrong. They are not colored. Okay, this is not painting. No, God has not painted them like, oh, you are red colored quark, oh, you are green colored quark. Not like that. God hasn't done anything. It is us. We are solving a discrepancy in a theory, thereby introducing a new quantum property. This is a hidden quantum property. Now, if a particle or baryon is made of 3 quarks, UUD, say 2U of different color, now the Pauli's exclusion principle is valid. Okay, so with the addition of color hypothesis, the Pauli's exclusion principle is saved, nothing else. Now we have one more thing, that is gluon. What is this gluon? Gluon actually it is the exchange particle between quarks. Actually there are strong forces between the quarks, and these forces are mediated by some particle that is called gluon. Like the photon in electromagnetism, it is photon is the mediator, and it's also a mediator. But there are very much differences between photon and gluon. Till date, 8 gluons have been postulated, 8 types of gluons. All are spin 1 bosons. Now actually they are like quark antiquark pair. We use springs to describe them. See how this happen. This is the red quark. This is red D quark. Now it gives up a gluon, that is RB dash. It actually then become blue D quark. Technically we can say that this red down quark has given up its redness to this gluon and become blue down quark. Then this red U quark absorb this redness and become blue U quark. So this is the exchanging property. This has been exchanged from this to this, and this exchange of RB prime gluon, the red become blue. Okay, so this exchange theory has been postulated only to explain the quark antiquark theory and the quark interactions. What are the experimental evidences? Yes, of course, there are experimental evidences that there are some mediating particles or mediating exchange particles between quarks. First one, the deep inelastic scattering experiment of electrons with protons, and second one is the electron positron annihilation experiment. In in that case the final product are hadrons. Now one question is also there: if there are experimental evidences of gluons, so there must be some experimental evidences of the quark particles. Yes, of course, there are experimental evidences. I have not shown here. Actually, the Rutherford cross section calculation of this electron positron annihilation reaction and the calculation of the uh, pion decay, especially pi naught decay, the calculation of the decay rate of that experiment, these experiments showed that yes, there are some more point like particles other than elementary particles what we know, proton, neutron, etc., etc. Yes, there are some more fundamental particles involved in those reactions. They suggest that yes, there are quarks, and these experiments suggest yes, there are some exchange particle through which quarks interact with each other. Now the main question comes, the most interesting question of our quark theory: do free quark exist? Actually, experiments are carried out extensively from that 1963, from the beginning, to capture a free quark. Experiments of two types. First type is in lab, high energy labs, by collision at accelerators, and second type is a search for pre-existing quark. Pre-existing quark in soil sediments and of sea, uh, the sediments of oyster, the cosmic ray shower, the moon rock or the meteorite rocks, everywhere they are the pre-existing quarks, if there are some free quarks obviously, but till date none have discovered any free quark yet. So experiments are going on, but there are some very interesting facts. Why till date no free quark have been discovered? Because it is believed to have confined very deeply inside the hadrons and cannot be isolated till date. Since none have discovered a free quark, so scientists have believed that they cannot be isolated, they are confined in the hadrons. But initially it was thought that they are a quark antiquark pair, gluon type, using gluon as a mediator. So if we can give enough energy to that quark antiquark pair, obviously they become separated from each other with enough energy have. Naturally that happened in particle physics. But what is interesting, that upon giving enough energy they didn't break, rather some other particle have emerged. Like upon giving an energy to a hadron, very high energy to a hadron, it's eventually become a meson, not a quark antiquark pair. What happened actually? See, this is UDD. Now we are giving enough energy to our UDD. What happened? This become excited with this enough energy. Now scientists believe that inside that UU bar is produced now. But then these 5 things rearrange themselves. Like we all know that meson is composed of 1 quark, 1 antiquark, then this U bar D and UUD. So 1 baryon plus 1 meson, no quark antiquark pair. That's why scientists have believed that this quark antiquark pair remains inside the hadron. It is so deep inside, it is so well confined with the particle that till date we are unable to free any quark, or we cannot find any free quark in the universe. The search is going. Hope someday someone like Higgs boson, hope someday someone discover and maybe awarded Nobel. So guys, this is the end of our lecture today. Hope you have liked it. Okay, bye. See you in next lecture.